Thus far, we've focused our attention on linear functions. Like I said, the majority of this chapter is about linear functions, but we know that there's a lot of functions that are not linear. We've actually seen them. Functions that are basically not linear, no surprise there, are called non-linear functions. These are basically functions that are not in the form y equals mx plus b, and there's plenty of them. We've seen them. So here's one that's obviously not in that form. This is a non-linear equation. It's a degree 2 trinomial, so we're talking about a parabola here, right? Parabolic, or what we're going to soon call a quadratic equation. Okay, so that's that guy. This is an absolute value equation. So we've seen those before as well. Their shapes have a distinctive shape. So it involves absolute values, so we call that absolute value equation. Take away the absolute values, it's now linear, right? But with those absolute values, it basically changes the formula, so we got that. H of x, again, this is clearly not a linear function. It's made up of a couple, right? The numerator is a linear function, and the denominator is a linear function that fits the y equals mx plus b. But together, since I'm doing a division, this is no longer linear, right? We learned this to be a rational function. Okay, so again, another example of a nonlinear function. Here we're dealing with a polynomial degree 3. I believe we called that a cubic, right? Earlier in the week when we were doing some graphing. So clearly it's not linear. The m is multiplied to x, and here this 3 is being used as an exponent. So it's not, this 3 is not the slope. So be careful. And then, of course, this last one, we have another example of a rational function. We're taking a polynomial divided by a polynomial. So, in effect, I gave you 5 examples, but nonlinear functions are anything that are not lines, or they cannot be represented in the form mx plus b. Now, what do we do with linear functions? The same thing we do with, what do we do with nonlinear functions? The same thing we do with lines. We can graph them, we can talk about their domain and range, we can use them to mathematically model situations. A lot of that's coming later in your math careers. But for now, how about we review how to find the domain? To find the domain, we learned a couple sections ago that all I need to look for are what I playfully called red flags, right? Is there any division by 0? Let's rule those out. And are we taking the square root of a negative number? If we can establish where these two things happen, we pretty much know what's not in the domain, and by default we know what is in the domain. So kind of reviewing that, when I look at this first one, I don't see any square roots, so that problem is handled. And technically speaking, the denominator is 2 or it's 1. It's definitely no opportunity for there to be a division by 0. So we said in the past there's no red flags, no problem areas if you would. So what's my domain? Nice, strong function. It's defined for everybody, negative infinity to infinity. G of x is an absolute value equation. Again, there's no radicals in it, and there's definitely not an opportunity to divide by 0 because this is all over 1. So therefore, there's no red flags again. There's no problems to worry about. So my domain is nice and strong. It's defined for everybody, negative infinity to infinity. Looking at our next rational function, there's no radical, there's no square roots, so we don't have to worry about that problem, but our denominator has x plus 2 in it. So we definitely have to worry, I don't want that denominator to equal 0. And so x cannot be equal to negative 2. So how do we define the domain? Well, maybe drawing a picture, right? Negative 2 we're throwing out of the domain, but that means we can be everybody to its right, and we can be everybody to its left. So we have 2 intervals. Negative infinity to negative 2 is this interval. We're going to union it with the negative 2 to infinity on that side. So there would be the domain for that particular rational function. For my cubic, again, there's no square roots, so we don't have to worry about that problem. The denominator is 1, so we don't have to worry about division by 0. So no red flags, no problems. Nice, strong function. Negative infinity to infinity. So we are defined for everybody. And then last but not least, we have another rational function. We do see a variable down in the denominator, so we kind of have to worry about I don't want that bottom to be equal to 0. And this doesn't factor, right? We know how to factor the difference of squares, but the sum of squares doesn't factor. And then if I even try to solve, this is what we're going to see in chapter 10, so another sneak peek at it. If I move that over, this part right here makes no sense, because we're trying to find a number that when I square it equals -4. And the candidates could be 2, but 2 squared is 4, and it could be -2, but -2 squared is 4. So in reality, there's not a number that I can square to get -4. So this means that this problem doesn't happen. So we accounted for it. We see that there's nothing that's going to make the denominator 0, so there's no red flags. So again, we have a nice, strong function. The domain would be everything. So hopefully that's a good review of some functions we've seen in the past, right? But and how to find their domain. And I think I told you back in the day what we need to do is we need a graph to find the range. Absolutely, positively need a graph. So that's what we're going to do in the next video. All right, we're going to review how to graph some of these, and then once we have the graph, we'll be able to establish and see the range. See you guys in the next video.